And it's not, when you look at this picture and it's like lifting on the windward side and descending on the leeward side, that would be the case of like the Continental Divide on a big scale. On a smaller scale, where you're just looking at a single mountain range, you're going to get overlap with the precipitation. It doesn't mean that Targhee gets a lot more snow than Jackson Hole because it's on the west side and Jackson Hole is on the east slope. There's a lot of storms where it's equal, or sometimes Jackson Hole will actually get more snow than Targhee. Okay. So that's sort of your basic orographic lifting. This is two pictures, one looking straight at the Tetons from east towards west, and one looking down. This is Blacktail Butte, and looking southward in the valley. And this was a weekend or so ago when it was just pure orographics. We had enough air pushing up against the mountains that it was lifting and making clouds and making snow in the mountains. If you sawed the Tetons down or leveled them down to the same elevation as the valley, in Teton Valley and Jackson Hole Valley, took the Tetons out of the picture, there'd be no clouds. It'd be blue overhead just like it was over the valley. Because there's no lifting mechanism. There's nothing forcing the air up. So the mountains are doing their work, and the Tetons are a great range for doing that work because they have 7,000 vertical feet of relief at the maximum anyway, more like 4,000 on the average. So but it doesn't take much. It doesn't take a lot of elevation gain pushing air upslope to get it to make clouds and make precipitation. But the key is that you have to have air moving perpendicular to the orientation of the mountains. And if the air is being, in other words, the flow of air is perpendicular to the orientation of the mountain, then I can maximize that lifting process and maximize the orographic enhancement of precipitation. If it's kind of hitting it at an oblique angle, that's still pretty good. It does a good amount of lifting. But if it's parallel, if the wind flow is parallel to the orientation of the mountain range, there's really no enhancement over the mountains, so to speak. And usually in this case right here, if the flow is perpendicular to the orientation of the Tetons, then the valleys on both sides will get almost as much snow as you do up at the higher elevations. Okay? But when I'm in this mode here, then definitely the mountains, if you go up in elevation, you're going to see more snowfall occurring. Okay? So for the orientation of the Tetons, which is pretty much southwest to northeast, kind of west to northwesterly flow direction is best. In other words, that's where I want my air coming from. Okay? So how do I get the air to come from that direction? Well, if you looked at this mountain range here, and just say it's a north-south orientation, and I have an approaching low-pressure system, storm system, that has a counterclockwise circulation around it. Just take my word for that, at least in this hemisphere. Okay? As that low approaches, it's going to do most of its lifting where the flow is, again, perpendicular to that range. So it's going to be the southern part of this low that's going to do, I'm going to have flow going up the hill. On the northern end of that low, it's actually going to be pulling air down off the mountain. So the air is sinking. Remember, the air's got to go up to make clouds. If it's coming down, it isn't doing anything. Okay? And then once it crosses over the divide, let's say, or over the mountain range, and then the flow up against it is in the opposite direction, then to the north of that low pressure center is where I'm going to get the best orographic lifting, and I'm pulling air down off the mountains to the south of that low. So where that low goes is really important to us when we're forecasting weather for the Tetons or for any mountainous area. Is finding out, being able to locate where that low is. And most of the time, low pressure centers are going to approach from the west here. They have a hard time crawling back over the divide, although I've seen it happen from the east. But basically, if you had a low pressure system out here by Boise moving inland, and I had a counterclockwise circulation around that, then it's going to kind of get oriented right up the Snake River Plain. And that's going uphill. It's very slightly, but it's going uphill. And what's right up at the head of the Snake River Plain? You got places like Island Park and West Yellowstone. very snowy places. So they're getting some orographic lifting through the Snake River Plain. As that low moves, say, further to the east, it's going to maybe line up over southeast Idaho, and I might get a flow direction coming from the southwest, which is actually good for the Snake River Range right here, maybe the Big Hole Mountains here, and even into Jackson Hole. But that flow around that low, when it's positioned there, is pretty much perpendicular, parallel to the orientation of the Teton Range, right? So it's not going to give the best orographic effect. And then that low, if it's passing to the south, due south of us, maybe you'll see more of a southeast flow coming around that. So that's when Bondurant would pick up most of its heavy snowfall, is when the low is passing to the south of Jackson Hole, and the circulation around it would kind of drive that lifting right into between the Wind River Range and the Wyoming and Salt River Range right in here. This is going uphill as well. And once it reaches that crest, then the air's going up over the hill and starts to descend. So we don't get any snow at a low when it's to the south of us here, but Bondurant's picking up quite a bit. Unless this is just a huge low pressure system, then everybody's good. And when you have a really big low pressure system, it kind of overrides the orographic effect because it's providing enough lifting that everybody's getting snow. So those storms where, oh, it's snowing in Afton, it's snowing in Bondurant, it's snowing in Jackson, it's snowing in Victor, it's snowing everywhere but Sun Valley. Never snows there. Ever. So that's okay. So then that low continues to move further east, and once it starts to cross over where the Continental Divide is, then the circulation is coming from the east, coming up against the eastern side of the divide. That's when Lander gets most of their snow, as that low slides across the southern part of Wyoming. And that's what they call upslope flow against the east side of the divide. Upslope storms that you get out in the plains, big low out there, into the Bighorn Mountains. That's when most of the rest of Wyoming is getting snowstorms and blizzards, is when that's going on. And we're over here on the west side of the divide going, another bluebird day. Those poor people. Anyway, so it's not that, Denver stole our snow. It's just where that low went, and it passed south of us 9 times out of 10. So what we want to do is we want to see those low pressure systems pass to the north of us. Head right over Bozeman. That'd be perfect. Okay? Then I'm going to have a counterclockwise circulation around that's going to actually bring me a flow that's going to be perpendicular to the orientation of the Tetons. And that's where I want to see those lows go. If they're going north of me, I'm going to up my snowfall forecast. If they're going south of me, I'm going to say, we'll get a little bit as that low's spinning across the Snake River Plain, but as soon as it's due south of us and moving east, we're done. It's over. Forget it. And that's what happened yesterday. We got a low right here. Oh, actually, Sun Valley did get some snow. Very odd occurrence. And so the low was right in here, kind of moved right over Sun Valley, and then it kept going right down here over Salt Lake City, and now it's down over the Four Corners. And so by the time it's right here, the flow is coming back this way. And that's why it cleared out at the end of the day yesterday, because that low went from here to here. Done. Over. Forget it. Okay. Again, it would have to be a very big, very powerful low pressure system to see a lot of snow from a low that's passing to the southwest. All right. So there's the Teton Range, and again, the northwesterly flow direction is the perfect orographic direction. If you went over to the Wind River Range, they actually have the opportunity to get a double whammy out of it. If it's a southwest flow, the western side of that Wind River Range will get a lot of snowfall, a lot of orographic lifting. Low passes by, and then the flow comes from the northeast, and they get it again. It's right on the Continental Divide, so it's different flow directions that will affect either side of that mountain range. Again, the Big Holes and the Snake River Range, Palisade Range, they're oriented for that southwest flow, and they do get quite a bit of snow down there. That's where we used to do a lot of our helicopter skiing, was right down in here. And I can tell you from digging snow pits down there for 20 years, that at the same elevation down here as in the Tetons, there's 25 to 30% more snow down there. I shouldn't tell you that because now you're all going to run down there and go skiing. Okay? But that's because of that predominant southwesterly flow direction ahead of an approaching low pressure system, which has usually got a lot of moisture. Okay? So southwest flow can be very moist, but it's not going to be the ideal direction to create a big dump of snow in the Teton Mountains, at least. But it is good for the Snake River Range and places like that. The other thing, we look at the terrain around here, and again, the red dot in the middle is Jackson. That's kind of the long axis of the Teton Range. And there's the long axis of the big holes and going into the Palisade Range, just south of Teton Pass there. And that makes kind of a natural V, if you will. And air moving from a north-northwest direction actually converges right there on Teton Pass. And again, right as you're coming out of the Teton Valley towards Victor, you're going uphill. So you're already starting to lift the air because you're moving it up the mountains. And then the two mountain ranges actually confine the air as it's moving in, so it converges the air. And anytime I squeeze the air like that or make it converge, it also makes it go up. So I'm lifting as I go up towards Teton Pass on the west side, and I'm forcing it into a narrower constriction from these two mountain ranges. So I'm forcing it up from the sides as well. And in this situation, when I have that exact flow direction, that's when you'll see maybe 6 inches of snow in Victor. You'll get a foot of snow on Teton Pass at 8,400 feet. And you drive down the other side into Wilson, you'll have traces of snow. Very unique orographic enhancement zone there. It's what we call a terrain convergence zone. And it's the terrain that's making the air converge and making the air go up more, both from lifting of the terrain of the valley, going uphill towards the pass, and the mountains, lifting it and confinement of those mountains there. Okay. So that's kind of a unique situation. That at the same time, the village might report 6 inches, Targhee might report 6 inches. And then you drive up the pass and go, ooh, you got a foot. If you did, that's what happened. This is a very difficult situation to actually forecast for. But when I hear or go see for myself that there's way more snow on Teton Pass than anywhere else, then I at least know why, what caused it, what's the mechanism. And that's usually what it is. It's that convergence zone of the Teton Valley moving up into Victor. So they don't always get more snow there. It's just in that certain weather situation, that certain flow direction has to be pretty much right on. You move that off of that 10 to 15 degrees flow direction, and it's over. They're not getting it anymore. If you look at Targhee and the snow that they get, when their snowfall is enhanced is when you pretty much have a westerly flow that lines itself up with Alta, not Alta, Utah, but Alta, Wyoming, and right up Teton Canyon. It's that westerly flow is passing over the low end of the big holes. So it's not quite unobstructed, but much more so than if it was down here. And then the other thing that's going on is you're getting some terrain convergence up Teton Canyon towards Targhee. So there's extra lifting going on there. Extra lifting, extra snow. That's the formula. Okay. So when you look at what's the flow direction is what I'm trying to figure out every morning. That's what's most important to enhancing that orographic precipitation. You might see 6 inches of snow in Alta. You might get a foot of snow at Targhee, and you again have less snow in that particular situation, maybe at the Jackson Hole Mountain Resort. If this is a really strong westerly flow, then with a lot of moisture in it, then maybe Targhee gets 18 inches and the village gets 12 or 14. And if it's pretty widespread geographically with that westerly flow and has a good supply of moisture, then with a westerly flow we can actually get a lot of snow in Jackson Hole from that, in the valley. So that's why I put a question mark for the valley. Some situations you might get an inch or less, or a couple of inches, where the mountains are getting multiple times more snow than that. And other times it'll be kind of an even distribution. I'll show you some maps of some storms that we've had where it was even distribution and uneven distribution. But let's look at, so to talk about the snow climate. That's what causes it, but this is the reality when you look at the annual snowfall numbers for different locations around the valley. In the town of Jackson, this is on an annual basis, not a winter basis, but it's not that much different. So it's basically going from January 1 to December 31st, so it's really encompassing a couple of winters. We average about 75 inches of snow in town. And last year we had, in the paper, I think I put 85, but it didn't include December, and I got December's numbers the other day, and we had 18 and a half inches in town in December. So 75 and 18 and a half, you do the math, okay? So it's above normal last year, okay? If I just go 12 miles north to Moose, where park headquarters is, that's that yellow dot on the map, they get almost 100 inches more than we do. And I can tell you from all the days of skiing and hanging out up there, you go just another 3 miles north, up over Windy Point Hill to Beaver Creek, where the old park headquarters used to be. And you could probably add another 50, 60 inches on top of that. It's unbelievable. A few hundred feet of elevation and a little bit closer to the mountains. That's the only difference, okay? Then I go up to the south gate of Yellowstone, and I can pile on almost another 100 inches on an annual basis up there. And then, of course, the mountains, well, the marketing report will tell you they average 500 inches. I'm going to say 400 to 500 inches. But that's still, if you look at 500 inches or say 450, let's average it out, that's 6 times more snow than we get in town. 6 times, that's a lot. So that's the power of orographics. It's multiply it by 6, and that's what you have up at elevation, okay? On the average, annually. Right? If I go to the other side, Idaho Falls, why it's not a ski town, they only get 35 inches of snow there a year. That might have something to do with INL, I don't know. Maybe more melts before they can measure it. Sorry, I offended anybody with that. Just a theory. But then I go to Driggs, and they get about what we get here, a little bit less in Driggs than we get in Jackson. But what's amazing to me is you look at the climate data from Driggs, and then you go up the hill to Alta. And what is that? That's a 5-mile drive. And it can't be more than a few hundred feet in elevation going up there. You can almost double what Driggs gets, 110 inches. Okay. And then looking further north, as I go up towards Island Park, they get 211 inches up there. Again, that predominant southwest flow lifting up onto the Yellowstone Plateau. Old Faithful does them an inch better, and that's basically on the west side of the divide, or right on the western side of the divide. Cross over the divide to Lake Yellowstone, and they're pretty much, Old Faithful and Lake are pretty much neighbors, and you can carve off another almost 50 inches of snow, 40 inches anyway, off of their annual snowfall there. They're on the east side of the mountain. So they're not as affected by that southwest flow that's lifting up onto the Yellowstone Plateau at Lake as they are at Old Faithful. So that's kind of the rundown of annual snowfall. This map comes from a computer-generated climate data set. And basically, it takes all the known instrumentation that's around and then extrapolates it to elevation and gives you sort of the what the average annual snowfall should be for different locations. So you can see where Jackson Hole is, you can see where Targhee is, and they're both kind of right in the blue here, between 400 and 500 inches. If you go just south of Jackson Hole, you got a little bit higher elevation mountains there, and they get more snow. And just west of there, it's a little bit snowier. So if you're looking for a lot deeper powder, you want to stay in the pink area, dark purple to pink. And of course, a lot of this is driven by elevation. When you get up into the higher Tetons, it's just extrapolating data from Jackson Hole and going up another couple thousand vertical feet and adding more inches of snow. But as we know, the wind blows pretty hard up there, so it makes it kind of hard to measure snowfall up there. And there's not, there aren't any instruments. There's one at Pine Creek Pass, but there's no instruments in the Snake River Range at all. So this is not like this because this map kind of keeps that quiet. You get a lot more snow. This is actually, there's a lot more snow in the Snake River Range at the same elevations. I bet you that would be pink or purple to pink up there, right in here where the Snake River Range is. And then anything that's kind of in the brown or tan is less than 100 inches annually. So that's, this is again just the computer-generated climate data is what it is. So all that snow, somebody's got to forecast every stinking inch, and I got elected. Of all the things I do forecasting, forecasting the snowfall amount is the most difficult thing. So for 8 months of the year, I have to wrestle with that. This year it actually started at the end of August, and what was it, 2010, 11? I was counting inches into the end of June. It gets old, it's tired. How great I didn't used to be this great, did I, Rennie? Not back when we were climbing. Everything was great. In the summertime, the biggest challenge is forecasting probability of thunderstorms. But in the wintertime, it's definitely, I spend an inordinate amount of time trying to decide what I'm going to say about how much snow we're going to get. And I know in a ski resort town like Jackson Hole, you have to be very, very cautious about what you say. It's very easy for whatever I throw out there to get misinterpreted. And I don't want to ever really overshoot it. I have this quote on my wall in my office. I have one other one I'll show you in a minute. But I look at it every single day. And almost every day in the winter, when it's not snowing, if I show my face in town or in the ski area or on the pass, somebody who recognizes me will ask me, when is it going to snow? And then once it is snowing, they want to know how much we're going to get. And then they start taking whatever I say and putting it into their own dreams, what it's going to be like. And if I say 6 to 10 inches, instantly that's interpreted, it's going to be like a foot, man. It's going to be a foot. What do you say? We're going to get a foot. If, like, say over a couple of days, I'm forecasting, 6, 7 inches here and there, and it totals up to maybe 14 to 18, that's 2 feet. Anything over 18 inches, that's a couple feet. It's going to be like this, it's going to be like that. It's going to be great. It doesn't mean diddly. That's quantity. There's a quality factor to snow, too. You want 18 inches of heavy, wet snow? No, you're dreaming about nice, light powder that's going to billow over my head in the cold smoke, right? By the way, did you check that guy's beard? And then about 20 minutes after it stops snowing, it all starts again. It's snowing. How much are we going to get? On and on. That's the way my days go, all winter long for 8, 9 months. Well, it turns out that I ask myself the same questions every day in a little bit different manner. First thing I do when I sit down to forecast is I ask myself if it's going to snow, and if so, when is it going to snow? In other words, when's it going to start, when's it going to stop, and then how much are we going to get in between that start and stop? And so those are the 3 main questions I end up asking myself every single morning in the wintertime. And I have my own little checklist of things that I look at through the morning. I look at a lot of current data to analyze the current situation, and then a bunch of different things that I make sure I look at every day as far as computer model data. And it's about a 3-hour exercise for me. I start at 4 o'clock in the morning, and by 7 o'clock I have to have something posted on the website and be ready to go on a local radio station at like 7:40 now. It used to be 7:10, so I've got a little breathing room. But you know, it's a constant battle looking at maps and trying to digest all the information, because it gets a little bit overwhelming. But what I start with are things like, you know, the satellite photo and surface maps and upper air maps and radar, things that are real, things that these are maps that are depicting the weather now, or the weather that's been going on over the last, say, 12 hours. So I can see what the weather situation is, see if, do I have a low pressure system that's going to go by the north of me or south of me? Where is it right now? What's the flow direction right now? And I can get all that off these maps. I can see, you know, where the moisture is on the satellite and radar to see if that's kind of lining up with things. So there's a lot of maps that I look at that show actual data that depict what's the state of the atmosphere is right now or over the last 12 hours. And weather observations and the instruments and things like that. And I'm starting to, you know, dissect things basically from the surface all the way up to jet stream level, around 35,000 feet. That's where most of the weather is going on. And so, you know, winds are important to me up there at the jet stream level. And then, say, from 500 millibars or 18,000 feet down, I got to look at a lot of other things besides just wind, looking at temperatures and looking at how much relative humidity or moisture is in the air. And then I get down near the surface and it gets kind of muddled when you get down there. But basically, I have to analyze a lot of different levels in the atmosphere to make my decision about what's going to happen. And then the next step is to turn to what the computer models say. What they do is they take those initial conditions, what the current state of the atmosphere is, from all these different inputs, all those different maps you looked at, including satellite and radar and surface observations and things like that, are all getting inputted into these computer models. And then they, you know, crank out what's going to happen into the future. And they take these different, there's a bunch of different types of computer models, and there's probably 7 active ones right now that are constantly analyzing the atmosphere throughout the day, 24 hours a day. You know, they're updated anywhere from 3 to 6 to 12-hour updates on these computer models, taking an incredible number of inputs of various weather phenomena that are going on. It's actually mind-boggling how much information goes into it. You would think that they could do a pretty good job of moving that weather forward and making a forecast out of it, but it turns out they don't. There are more what they call high-resolution models, which take a kind of a limited geographic area and try to stuff more input into it and get a more accurate forecast that way for a smaller geographical area. Some of these models are running a global data. So they're taking data in from all over the globe constantly and inputting it into this thing, and then, you know, forecasting for a small point on the surface of the Earth. Okay. Well, I'll tell you in another little hint, there's a lot of data voids in the world. Like 75% of the Earth is water. Maybe that number's a little off. There's not much data coming from those. There is some now. There's more now than there used to be with buoys and instruments in the ocean. But it's mainly land-based observations that we put in. There is satellite stuff that's going into it. And then it'll crank out a global forecast of, say, winds or the wind flow pattern. This is a jet stream pattern for the globe based on that model that inputted all that data. Okay? So then I go through the next part of my routine is to go through all these weather maps that go into the future. They're kind of the same looking weather maps for all different levels of the atmosphere, analyzing different variables as I go from the jet stream level all the way down to the surface, and move that through time. And you can get as detailed with that as you want. You can get models that give you output every hour, or you can look every 3-hour increments, 6-hour increments, whatever the case may be. And that gives me an idea of if, it kind of gets me in the ballpark, let's say, by looking at all these different weather products, forecast weather products, okay? So it gets me to answering the if and the when. I pretty much do that, but the how much is where it really gets ugly. And computer models handle like wind flow direction, maybe how much moisture is in the upper levels of the atmosphere, and the temperatures in the upper levels of the atmosphere really, really well. When you get down close to the surface, they do a really poor job of predicting temperatures, and they do an even worse job of predicting how much precipitation you're going to get. In other words, how much of that moisture is in the upper levels of the atmosphere can I wring out and put on the Earth. Okay? So the how much is where I'm going bald. Trying to figure that one out. So all kinds of products that help you. This one will show me where it's going to be rain or snow, and then it'll show me how many inches of either snow or water I might get, whether it's going to be a rain-snow mixture. It's got a whole bunch of other squiggly lines that mean something on them, but at least the colors are easy to dissect as far as how much moisture and what type of precipitation it's going to be. White or blue is snow, and pink is some kind of mixed precipitation. Green would be rain. Okay? And there's also, from these computer models, I can actually generate a snowfall forecast from the model data that'll tell me how much snow there is. But all of these maps here, they're predicting amounts of snowfall in inches, are all based on the water amount that's going to be forecasted by those same computer models. So I always go back and look at that first before I consult any snowfall forecast maps. And like I said earlier, there's probably seven different working models right now. There's two that I consult more closely than others. One being the North American mesoscale model, and there's different versions of that. And then the Global Forecast System model, GFS model. But if you look at these, both of these, this is model output predicting how much water amount we're going to get for a 3-hour time period. And the NAM on the left is showing that I could get 1/3 of an inch of rain where it's red in 3 hours. And the GFS, it'd get nothing. Who's right? Well, on any given day, either one of them could be right. And one of the problems you run into with the higher resolution model that you get, it actually is taking data from the lower resolution or larger scale models and forcing it into these higher resolution, smaller geographic area models, and it misses stuff, or it misinterprets stuff. And I didn't go get my master's or PhD, so I really don't understand exactly whose math is in there and what it's doing. And I hated differential equations with a passion. So that's one of the reasons I never went beyond getting my BS. But a BS is good enough for telling other people what the weather's and how much snow you're going to get. Because that's basically what you're doing. There's some newer stuff now that meteorologists are utilizing to help with this problem of, the models just don't do good with precipitation. So what they've done is they put together these ensemble forecasts, and what they do is they look at about 7 different types of models and just, kind of throw it all into one big pot and stir it up and see what it pushes out. And what it pushes out is the probability of snowfall, and you can get different amounts. It's like, okay, I want to go, what's the probability of us getting 2 inches or greater in the next 72 hours? And the probability numbers are over here. So North Texas, very high probability. down around the Four Corners, also very high probability of at least getting 2 inches. 2 inches is nothing. Let's get to the real stuff. What's the probability of getting 18 inches or more in 72 hours? And the only place right now that has any potential would be Whistler. Anybody needs to leave? I think there's one more flight out tonight, I'm not sure, but over the next 72 hours, that's the only place in, this part of North America that there's the potential to get more than 18 inches in the next 3 days or so, okay? And I can show you where these maps are. But this is the other quote I have on my wall. And I always refer back to this because it's so easy when you're looking at these computer models and they start showing, oh man, look, there's a foot, there's 18 inches, it's going to be great. Calm down, will you? These are computer models telling me what it's going to do. This isn't reality, okay? And Sir Napier Shaw, who wrote the Manual of Meteorology back in 1940, recognized this right off the bat, before the first computer model was even run in the 50s. That's the way he completed that. And I pound this into people when I teach weather classes. You're looking at computer models, you start believing what they're showing you. You read a forecast, you start believing what it says. It's a fairy tale. It may not come true. And a lot of times it doesn't. A lot of times it does. A lot of times it gives you more than what you thought it would. And a lot of times it gives you less than what you thought it would. And when it comes to snowfall forecasting especially, I put that forecast out, and as soon as I punch the button and publish it, I know it's probably wrong. Somewhere it's off. And it depends on where you are. I mean, to forecast for the whole Jackson Hole Valley, you saw what the snow climate is here. If I say 2 inches in the valley, well, town might get a trace, moose might get 6 inches. If I say 8 inches in the mountains, well, let's say I said 8 to 12 inches in the mountains, just to kind of give it a little range, right? And you're skiing at Targhee, and they get 6 inches. Is the forecast wrong? No, because I'm going to drive to the pass, and they got 12, and so I'm right. But the problem is that if I say 8 to 12, and then people get up in the morning, they look at the ski report, and they report 8 inches. I go, all right, that's right. I'm going to mark that as a correct day. And I go out and talk to people, they're like, hey, where's the other 4 inches? You said 8 to 12. We see that as sort of the middle. Okay. But it's all about the flow, and that's what I fall back on. After I go look at all these computer models, I go back to looking at the flow and looking at where it's coming from. And I know from my experience that southwesterly flow is going to be a fairly even distribution between higher elevations and town. Sometimes it's more in the mountains, for sure. But I can also tell you, if I back up here once, if I move that arrow and make it more of a southerly flow, that's when Snow King gets the big times. And so don't get up in the morning in town when there's a foot of snow in town and think instantly, there must be 3 feet at the village. I gotta get there, I gotta get shoveled out, I gotta get out there, I gotta get on the bus, I gotta get to the parking lot, I gotta be the first guy in the tram. They're gonna have the same amount of snow. Go to Snow King. Southerly flow, go to Snow King. They'll have as much snow as they're gonna have at the higher elevations in the Tetons with the southerly to the south. Southwest to south flow. If I have a big low pressure system, 2 lows right here, covering from British Columbia to Mexico, and giving me kind of a west to southwest flow, that's going to be a kind of situation where it's a big storm, even distribution. Mountains will get 15 inches and town will get 13 inches. Okay? So you're not going to get a whole lot more going up in elevation, but good for low elevation power skiing for sure. It's more of this west to northwest flow that the mountains actually, that's when our best orographics kick in. So that's when we see the biggest discrepancies in the amount of snowfall between, say, the valley and the higher elevations in the mountains. And that's, again, when that low pressure system is passing by from the north, across the Idaho Panhandle and into western Montana and beyond. that's also helped somewhat by a ridge of high pressure here that's accentuating that flow that's following those red lines. But the real kicker is, in the best, absolute best snow does not come from storm hole. And that's when we have the northwest flow. Storm's way out here in the Gulf of Alaska. I got a ridge of high pressure here along the west coast. If the flow is pretty much parallel to these black solid lines, and it lines up coming over the top of that ridge, so it's bringing warm, moist air up into the Gulf. This low is circulating cold, maybe drier air down like this. That combines here, the moisture with the cold, comes right down over us in a northwest flow. That's when we get that nice light density powder, the cold smoke, the best snow possible. You'll get a foot of snow in the Tetons, and usually less than 2 or 3 inches in town during that exact situation there. And that's with no storm. This low is real weak, and it's already east of the divide, so it has virtually no additional effect of lifting going on here. This is just pure northwest flow orographics. Just had a week or so ago. Often referred to as a dirty ridge. It doesn't have anything to do with porn or anything like that. It's just a term because the ridge out here has a lot of moisture moving over the top of it. So it's actually moving through a ridge of high pressure, sinking air here with clockwise circulation, and then counterclockwise here, combining with clockwise here to make the ridge bulge up and then comes down in the northwest flow. So it's almost guaranteed cold air, which is going to produce lighter density snow. As long as the winds aren't too strong, it will just, fall as very, very good powder snow. So the best storm is not a storm, as far as I'm concerned, for good quality and quantity of snow. Okay. So it's that flow interacting with the terrain that drives the whole program. And so I'm constantly watching to see how that flow direction is changing, and that's going to affect my forecast through time as it goes. And anything coming from the north or the east, I know that it's going to affect the other side of the divide, and it's not really going to affect us much at all. Again, unless it's a really big circulation with a lot of push to it, a lot of moisture, but those are pretty rare. So this is my final product that I put out each day that's available on the website. And I know a lot of people just forget about everything that's on this except for this red box here that I boxed out, and they hone in on the big snowflake with the bars, and then they start counting up how many inches of snow we're going to get over the next few days, and we go on. That's 31 inches. Well, to a skier, that's 3 feet. Okay, automatic. Just add a little extra just to get to 36, and we're there, right? So the reality is, dude, that this snow is falling and it's settling. So you're not going to go out on Sunday morning and ski 31 inches of snow going over your head. Okay? And there's other things you want to watch for too. Is, what's the temperature going to do? If it's cold, it's going to be lower density or better skiing, better snow. If it's warming up, then it's going to get heavier and wetter, which is what we had happen this past weekend. Started out great, and yeah, give me 21 inches. Cool. Except it got really heavy and wet. Now skiing's not as good. So anyway, they're doing it out there, I know, and they have their own dream about what those bars mean. But hopefully you can make more sense out of it. And I always tell people this, that weather forecasts, they're not gospel, they're guidance. It doesn't mean that we're actually going to get 7 inches. I might, down here, I give you a little more detail. I'm kind of hedging my bets and going 6 to 9, but I got to put a bar in there. There's no way I put 9. If I'm forecasting 6 to 9 and I put a 9-inch bar on there, forget about it. That becomes a foot. It drives me crazy. It's always better in this town, and I get some flack for this one too, but to me it's always better to under forecast. I've never had anybody, if I forecasted 7 inches and we got 9 or 10, never had anybody complain. But if I forecast 7 and we only get 5 or 4, oh man, I suck. This is actually my favorite forecast, and when I retire, this is what it will look like every single day of the winter. It'll be a 50% chance of snow. That way, if it snows, I'm right. If it doesn't snow, I'm just as right. Look for that, it's coming soon. I don't have too many years left in me. Okay? There's a lot of other weather products out there, all available on my website, different links, but this is just another one. It's off of these computer models. It's point forecast data. You can pick a point, which is actually a box that's a couple square miles in size, but it's for roughly that elevation. If you look at this one, this is up near 10,000 feet. And hour by hour, it's showing you what the temperatures are going to do, what the wind's going to do, what the cloud cover is going to do, how much snow we're going to get. Hour by hour by hour. Very, very detailed. But I'll caution you that more detail does not equal more accuracy. Don't get hung up on it. Again, it's just guidance. It's not gospel. Okay? Weather Underground, I think this one's from. 10-day forecast. Well, the best models available, most accurate model available, only goes out 18 hours. The next one that's pretty good will go out 72 to 84 hours. So it gets you almost 3.5 days out. Once you go beyond that 3.5 day mark, you're into a different model that's a global model. And to get a 10-day forecast, you have to be using a global model like that. So the accuracy is going to just keep going down the further you get out. I will guarantee you that by the time you get to the 4th or 5th day of pretty much any forecast, unless you live in Hawaii or in the middle of the desert somewhere, that 4th or 5th day of the forecast is at a better chance of being wrong than it does being right. 3 days, the models do pretty good with, 3 days out. 4th, 5th day, the accuracy drops almost below 50%. 6, 7, 8, 9, 10 days out, forget about it. Isn't that what they say? Now, AccuWeather does the month by month, day by day. So this is February. If you want to just take a picture of that with your smartphone, you know exactly what it's going to do next month. A lot of products out there to look at. Again, remember, it's all fairy tale. And what forecasts really are is an expression of uncertainty. So when they say a 30% chance of showers, 50% chance of showers, it's saying that we're not sure that you're going to get it. But we all know that we've seen it snow here when there's a 30% chance of snow. We've seen it snow here when there's a 100% chance of snow. And we've seen it snow here or not snow here when there's a 70 or 80% chance of snow. So don't get hung up with the probability of precipitation. Read the forecast and figure out what the weather situation is and see if it's something that's favorable or not to what's going to produce snow here normally. And forecasts and computer models, it's just like different opinions. Everybody has a different opinion on it, and they do too. And it's the days when they all kind of agree with each other, the forecasts or the computer models, that you can have a lot more confidence in, yeah, we're going to get 6 inches or 8 inches of snow. But the days like that one I showed you where one model showing me 1/3 of an inch of water and the other showing me nothing, I can't have a lot of confidence in what's going to happen. So I have to fall back to what's the flow? Where's the moisture? Where's it coming from? How's that going to interact with the terrain? And that's my secrets. My dirty, rich secrets. Okay? But the skier, the discerning skier, he just is hunting for the forecast that has the most snowfall in it. And that's the one well, they said, or Woody said, or they said, whoever they are, said, we're going to get this. And that's the one they hang their hat on, which is cool. Go with that. Okay.
So we have a few minutes, a little bit of time to ask Mr. Woodmencey a few questions. There aren't any probably, right?
Let's start up front.
What's going to snow?
Presumed increases in improvements in remote satellites, infrared, and computer packages to crunch the fluid dynamics. How much better is this going to get over time, or is it kind of reached a plateau?
That's a hard question to answer. And actually, at the last International Snow Science Workshop in Banff this fall, some meteorologists asked that question: are we any better now forecasting snowfall or how much weather than we were 20 years ago? We have more tools to work with, and I think we can. We have more things to look at to help us make a decision than we had before. It's, back in the day, I can say that now, I'm old enough. We didn't have a lot of tools to work with, so you had to kind of use your local knowledge and say, okay, well, this is the flow direction. If there's enough moisture in it, I'll get this. Yeah, it's almost too many things to look at, and what happens with that is you suffer from paralysis by analysis. You looked at too many things, and now you're like, I don't know what to say. My wife can attest to that. She'll walk in my office right before 7 and say, what's the weather going to do today? I'll look at her with a panic. I don't know. I just spent 3 hours looking at it. I don't know. They try to make more detail out of it, but again, I don't think more detail is helping us that much, because it can still be wrong, even with that level of detail that we're at now.
What's the correlation between flow velocity and snowfall?
You need, for orographics, you do need to have some flow. You need, say better than 15 knots pushing against the mountains to actually get it to lift. Otherwise, it's just going to dam up against it or flow along the base of it. So, yeah, there's kind of a critical threshold there. And I'm looking, at 10,000 feet. I want to see it blowing, 15 knots, almost 20 miles an hour, to say that, yeah, okay, now I can get enough push.
What about cloud seeding? Did they do that?
They?
They.
I don't. They do. Yeah. The thing about cloud seeding is you need clouds to start with. It doesn't make its own clouds with the seed. And the silver iodide, burning silver iodide dust into the air. It has to have a cloud to start with, and it has to be a certain type of cloud, a certain temperature to be able to make it work. But it can produce snow. The problem with it is, as I understand it from what I've read about it, is you don't really have any control where it ends up. It may not fall out where you wanted it to.
What holds clouds together from the point of view of looking into a blue sky? Why is the cloud fractured?
Well, it's a whole bunch of water droplets that are forming or condensing, like sort of the condensation on the outside of your cold beverage can in the summer. And they coalesce together and make the cloud that we see, and the process keeps going until we have a cloud that's basically buoyant or suspended in the atmosphere because the updraft's holding it up. If the air is sinking just adjacent to that, which oftentimes it is, then you'll have a blue hole, a blue sky there. But when you look at a blue sky, there's a lot of water in that sky. But it's in the form of invisible water vapor. So you can't see it until it condenses into a water droplet.
Do you have anything to do with the airport in terms of forecasting? Or is that all national?
No, it's all national. Same with the Avalanche Forecast Center. That mountain weather forecast they have is coming from Riverton. So a lot of people confuse that with me. It's a different forecast. So there's another opinion. Yeah.
Tell us about this weather phenomenon we had last week. The ground level go up and freezing go up. But it seemed to be a little longer than ours.
Yeah, a lot of people have said that. And I know we've had Decembers or Januaries where it's hung in the valley here for days at one end. And basically not enough wind to move it out, high pressure sinking over us. If you remember what happened leading up to that, we had all that snow, and then it rained in the valley. So the lower part of the atmosphere in town and then throughout the valley was very saturated. And so as soon as it cleared, cooled, with high pressure pushing down, again, that's the only situation where I don't really have air lifting, but I'm getting cloud is when I have fog with high pressure. Yeah, yeah.
I wonder if you know any of the science behind the Grand Teton National Park weather forecast back in the 70s. We used to hike with a ranger friend, and each morning he had to get someplace where he had a line of sight, so he'd radio in and say he was still alive. And they give him a weather report. And you know, there were only 2 weather reports. 20% chance of rain, 80% chance of rain.
Yeah, that's about right. You got to hedge your bet a little bit, you know? And a 20% chance of rain means there's an 80% chance it won't. And vice versa, with an 80% chance of rain, there's still a 20% chance that it's not going to rain where you are. Joe?
Woody, it took several weeks longer than normal this year for Jackson Lake to freeze. And is that a large enough body of water to be able to create a lake effect snow? Yellowstone Lake certain years takes a long time. I mean, Great Salt Lake, are these big enough to?
Well, the Salt Lake is because, one, it's very shallow and it's got high salinity and it doesn't ever freeze. But what drives that lake effect snow is the temperature of the water. And since the Great Salt Lake is very shallow, it stays relatively warm all year long. Where these glacial lakes like we have up here, you guys can correct me if I'm wrong if I use the geology term like that. They're deep and they're cold. And I'm not sure why they took so long to freeze. I have some theories that maybe it didn't turn over. There's still warmer water on top. I don't know. I don't know that much about that. But the Salt Lake effect is a totally different thing. What you have to have is very cold air moving over a warm lake. And that's what a lake effect is. You don't get it without that. As soon as the lake freezes, it's done. Same with the Great Lakes. They get most of their lake effect snows in the fall before the lakes get too cold. And you move cold air from Canada, from the northwest, over those lakes, and that's, you know, they're warm. And I've got rising air over the lake, cold air, it makes it very unstable. Lots of lifting generated from that. Convective lifting is what it is.
There was a question over there.
Yeah.
Oh.
You talked about the continental divide and impact it has, and how does that change in like the Great Basin and the little internal Iron Basin?
You mean the Great Divide Basin?
Yeah.
The Great Divide Basin is basically a meteorological black hole. I've driven out to the edge of it and looked into it, and it really is no man's land. And there's no weather instruments I know of down there. But yeah, it would just be, since it's more of a depression than anything else, it's sort of just an avenue that things will just flow right through there, and not be impeded or lifted or anything like that. So it's really where the mountains are along the divide that's most important.
All right, I have just a couple of things here. Jim will be around for a few minutes while everything's taken apart here. Next week, Jen Pierce will be over from Boise State. She'll be talking about the opposite half of the year, basically the fire season, and some of the dynamics associated with fires. So, I mean, that one would have been better in summertime, but you take